When we look at single bit parity scheme, we apparently discarded it because we said it is not very robust and it adds redundancy to the data bits, which increases linearly. But using a smart strategy called horizontal and vertical parity scheme, we can implement the single parity scheme in 2 dimensions. In this module, we shall see how single bit parity scheme can be generalized into 2 dimensions. How can it help us to go for error correction as well? And then we'd also put a constraint or an upper bound in terms of its performance limitations. Gallagher and Dimitri discuss briefly about the usage of parity schemes and checksum. However, you can find significant details in Kuros and Ross. Single bit parity scheme can be generalized into 2 dimensions. If we take data bits, let's say D data bits, and split them into I rows and J columns. So we are actually looking at the same bit stream now in a planar way, in 2-dimensional way. Now we perform the parity check at individual rows and individual columns. So what we are going to get is I plus J plus 1 parity bits. Now, if we are going to get these many parity bits, are we going to get some advantage also? We'll see that shortly. Let's take the example of taking 49 bits. That is, we split it into 7 rows and 7 columns. We would require 15 additional bits for the end of every row and for every column. So apparently the redundancy we are getting is 25%. And if we keep on increasing the number of rows and columns, effectively this redundancy is going to reduce. Let's look at the operation first and then the advantage. We look at the data stream that we were seeing initially as a single row data into I rows and J columns. And we perform the parity check at row by row fashion and then in a column by column manner. And we also have to compute the column parity for the final column that we obtain towards the end of every row. Let's take the example that is shown below. We have 15 bits that we split as 5 columns and 3 rows. So we are going to get, in terms of row parity, 3 additional bits. But when we place them in row and column manner, we also have to compute the column parity and we get 5 additional bits. But the 6th additional column that we are getting, we have to compute its single bit parity scheme check as well. Now we are going to get 24 bits. Of these, 15 bits are the data bits and 9 bits are the parity bits. The advantage of using this parity scheme in a 2-dimensional manner is, let's take the example given on the right hand side. Let's say in the second row and second column, 1 bit goes in error. This single bit error is identified in the row and it is also identified in the column. If we look at the intersection, the row and column parity schemes refer to the bit which is at the intersection of these 2 schemes. Because of that, what we observe is that the bit that went into error is identified and all we need to do is just flip it, because now we see here that we are looking at a 0 in this figure, but initially it must have been a 1. That is why this particular row second row, and second column are giving the parity error. Their intersection is referring to the bit which is in error, and we can even correct it. So the beauty of using a two-dimensional parity is it gives us single bit error correction capability. Even if an error occurs in the parity bit themselves, it can be detected as well as corrected. This is termed as forward error correction, and it is one of the most widely used mechanisms deployed in storage media and over satellite links. The limitation of two-dimensional parity is that it can detect any number of errors, but it cannot correct if the errors are taking place at two different places.